this morning, well, our side, sorry, Lau. Yeah, this morning we're gonna have a presentation from Mr. Lau from SIGRAY. He's going to present and explain us what the technology SIGRAY can offer for the research, especially for the mineral research in Indonesia. And the audience today, Lau, they are from BRIN, is they're from Research Center for Mineral Technology. It's a part of BRIN. As you know already, that BRIN is a big organization and so many research center under one roof. So yeah, hopefully you can share with us all the information that you have or whatever SIGRAY can offer for enhance the research that can help all the researcher here for the especially for the mineral for mineral related research. Okay.
Okay, yeah, so can you see my screen?
Yeah, I can see that. Yeah. Well, without further
Okay,
ado, the time is yours, Lau, and for everybody, if you have a question, then we can have a Q&A session after the presentation. Yeah, you can just ask directly to Mr. Law, or you may be able to write it down on the chat session. Okay, right?
okay.
Uh,
So are you in Jakarta or in Bandung?
Gimana, Fafika?
I'm in Lampung.
It's in
Oh,
Lampung, Law. It's another island. It's
Another
very
island.
close. It's very close to Jakarta. It's another tip of Sumatra. The down tip.
oh, okay.
Yeah.
Uh, okay. So everybody from Lampung?
Uh, yes. Oh no, there's Bu Retno from Bandung and also from Serpong.
Oh, okay.
So because the research center was divided into 4 locations: Lampung, Serpong, Bandung, and Yogyakarta. So I think
Mm.
research, not only from Lampung but also from another city.
Okay, good. It's an honor to address so many of you. Even I was in Jakarta maybe a week ago. But it's not possible for me to go to Lampung and some of the other places.
Yeah.
So let's meet here. So a little bit about who we are. Our company is a very fast-growing company. Uh, what we do is we bring technology that is currently in synchrotron and transfer some of those techniques in the synchrotron to the laboratory. And the way we do that, that has helped us to be able to have the breakthrough is two major components in our equipment. One is a X-ray source that is tunable, meaning it has multiple energy. The other one is a X-ray optics that have the ability to focus X-ray beam into a tiny spot size without losing much of their flux or the energy. And this X-ray optics is also used by synchrotron around the world. So by combining this technology, that is this tunable X-ray source, uh, we have been able to get a very high flux as well as a small spot size with different energies. I'm going to explain to you what different energy means because most X-ray tubes only have a single target material. So like for example, you work with the tungsten target, then you have tungsten X-ray energy that is given off. If you change your material to rhodium, then you have rhodium X-ray energy. So that's how XRF, XRD, they have different X-ray energies according to what type of metal is in their target material for the X-ray source. But our system has the ability to change or switch energy within the same X-ray tube. So by changing by clicking your software, you can choose many different energies, just like what they do in the synchrotron. So because of this, we have been able to come up with many different X-ray or laboratory X-ray techniques uh, that has performance very close to the synchrotron. For example, today we're going to talk about AtoMap, micro XRF, but then this AtoMap has many different features and performance that is way better than the traditional laboratory micro XRF. And in fact, it has performance very close to the synchrotron micro XRF. We also have X-ray absorption spectroscopy for the battery people and for the catalyst people. We also have X-ray microscope to look at structural imagings of rocks and from mineralogy all the way to the explorations in the mine and the exploration of matters. And we have also X-ray microscopes for electronics, for battery research, for material science or biological sciences. So now about the AtoMap or the micro XRF, we have the ability to look at compositional mapping of elements at the micron scale. And we can detect elements that are so, let's say, what you call low concentration. For example, we can locate or detect residues of dose in semiconductor manufacturing that is a fraction of 1 angstrom. Normally, an atomic layer is about a few angstrom, but we can see changes in, let's say, a region or the area uh, of the sample that can detect leftover uh, atoms spread over some maybe a larger area. And our our system is used in battery and semiconductor research. Uh, we are also in the mining and the battery research using the micro XRF, as well as in agriculture, in food science, in medical science. Why? Because the X-ray fluorescence microscope can be used in such a way that it can get you elemental resolution of 3 to 5 microns and sensitivity of sub ppm, and we can detect things in the organic, things in agriculture or in the living tissues, and also detect all the way down to boron. So, at a glance, what is the technology? It has an X-ray source that is energy tunable. We can do light elements at even low detection level, including looking at carbon at the sub percentage basis. The elemental resolution 3 to 5 microns sensitivity sub ppm. And also it can be coupled to other type of tools. Like for example, we work with the German Geological Survey, where they put in a Raman in the tool. So we integrate or help integrate those type of equipment inside the AtoMap. So what is this X-ray technology and how does it work? uh, a little bit of background as to how X-ray is formed. X-ray is formed by having a filament. When you heat it up, it creates a charged cloud or a big cluster of electrons. And if you put electrons in a potential difference, this means the electrons are negatively charged. And if you make your metal or the target material positively charged, what happens is that you create a potential difference where the negatively charged electrons is going to accelerate towards the positively charged metal target. So when it do so, it is releasing kinetic energy, and the majority of the kinetic energy, maybe 99.99 or whatever percent of the kinetic energy, is given off as heat. A fraction of 1% can only be used to generate X-rays, and X-rays is generated in all directions. So that is how the X-ray tube is formed. You put a glass envelope over this target material, and this glass envelope is like the bulb. It is made inside is vacuum, and therefore the X-rays will come out from the window of the X-ray tube. So there's a conventional target of an X-ray tube, and how it is formed, how it will form X-ray energy. So if you want to have higher flux, or that means higher intensity of those X-rays, you can do it by increasing the power loading. What do you mean by power loading? This means increase the number of electrons that is going to hit the target material at any point at a measure in the unit time. And so as you increase the power, the acceleration will increase, and then X-ray intensity or flux will increase. But in life, uh, there is no free lunch. After a little while, you're going to hit a wall where you cannot increase the power loading anymore, because the material that you are bombarding with electrons is going to melt. So therefore, there is a finite amount of power loading you can increase in order to get more flux out of a laboratory X-ray tube. So how do you solve this problem? We have a pattern, and that pattern is this. If instead of having the whole block of metal to become your target, like all X-ray tube, what we did is that we embed tiny pieces of metal in a substrate that is very thermal conductive. So why? Because we want to get rid of the heat that is generated very quickly. So you can now increase the power loading to have more X-ray flux. So if you take a look at the material and their thermal conductivity, copper is a good thermal conductor. It can dissipate heat very quickly. But diamond apparently is 5 times better than copper. So instead of using copper, we now use diamond, so that when the electrons hit the metal targets, it will increase, it will generate heat, and the heat is quickly conducted away by the diamond substrate. So in that way, you can increase power loading. You can increase power loading by more than 5 times, and therefore you will increase your X-ray, let's say, illumination much higher. So we came up with the X-ray tube, and this X-ray tube will now have 30 times higher brightness than conventional micro focused X-ray tube. And the second thing is that we can create multiple energy. So instead of just having one array of a target material like rhodium or molybdenum or gold, we now can have one row of rhodium, one row of silver, one row of gold, one row of tungsten, one row of silicon, or different type of target material to put into a single X-ray tube. And you might be thinking that, wow, to put so many of them, the tube must be very big. But the truth is, the tube is very small. It is the size of two soda can, like Coca-Cola can, two stacked together. So that's the size of our X-ray tube. But this X-ray tube has the ability to generate multiple energies. And if you couple this with a X-ray optics, and we have the best optics in the world, we can create a focus beam that is less than 5 micron in spot size at high flux and efficiency. So What are the different type of target materials that we can support? We can do tungsten, rhodium, moly, gold, copper, chromium, silver. These are some of the choices that you can put into the X-ray tube, and we can support up to 5 different targets and different X-ray lenses together with it. So that is what it looks like in the side view. And you see that there are two motors here. One motor is to move the target when you say that I want to have Morley target. So this motor will move the target into the region where the electron beam is going to be. Then you say that, okay, I want to move to go. Then this motor will move the position to go. So that will be one axis of the target to control that. The other axis is to make sure that your X-ray target can have a long time, a long life, so that when it dies or when it get melted uh, or pitted, we do not have to change the X-ray tube. How do you do that? Because we have an array of target. What we can do is that we can move a small amount of movement to move the target from the region where it may have been pitted or is melted. We can go into the fresh area. So in that way, your tube can last longer. All right. What is the advantage of having multiple target? Let's take the case of, let's say, a few targets that you may have and look at some of the critical elements or elemental composition that we are trying to look at. So it, this is the table of X-ray fluorescence yield, or in other words, it is how much count can you generate out of that particular energy. So, like for example, if let's say I'm looking for aluminum, which is a soft metal, so if I were to use molybdenum target, which with the excitation energy of 17.4 kV at the K alpha, you find that it hardly excite aluminum. You may get 5 counts. That is not enough to really do any work. What if you change to a copper tube or copper target? Now you increase 10 times more, but at 51 counts, that's not enough to do anything. Then what if you now use a chromium target? Yeah, you may increase 30 times more, but it is not enough to do any work. So what if now you switch to silicon target? Wow, you can see that yeah, it has increased 644 times with 3,000 counts per second or something. That is enough to be able to collect enough signal in your spectrum to analyze aluminum effectively. So therefore, you can see that by changing energy of excitation, you will be able to quickly increase sensitivity. Why is this important? It is important if you have trace minerals. Like for example, if you're looking for rare earth, right? Looking for gold, all these have a very trace level in nature. So therefore, if your system doesn't have enough ability to excite those fluorescence, you will not be able to find them. So let's take a look at an example of mining. Let's look at gold. If I want to look for gold in a piece of rock, you can come with a huge chunk of rock. How are you going to find that tiny gold? Gold has native abundance of around 1 ppm, 1 parts per million. So it is not easy to locate gold if somebody brings you a piece of rock. So what can we do? We can do what the MLA or other techniques do. You look at the associated minerals, and if you can locate a associated mineral where gold normally co-locate within the sample, you might have a much better chance and much faster way to find that gold particle. So what we look at is, let's say if I use a tungsten source, I want to look at the association of gold with tungsten, go with another mineral. So you know that in the geology, gold is normally found in association with materials like arsenic or materials like pyrite. So why don't we start looking for this type of particles? So in this case, if we were to look at arsenic using a tungsten source, you hardly can see much fluorescence out of that because arsenic is not a good energy to excite. No, tungsten is not the good energy to excite arsenic. Now, what if I change my X-ray excitation? I change that to a molybdenum. So molybdenum at 17.4 kV suddenly have the ability to excite the gold fluorescence. So excite the arsenic fluorescence, not the gold yet. So therefore, you can see that there is a lot of arsenic in this sample. And once you located the arsenic, now you can scan again to look for gold. So that will be one two-step way to localize something that has very low sensitivity. It is low in sensitivity simply because the amount that is found is very small quantity. So that it will be one of the techniques having the tunable target to be very useful for many application. So the next thing, let's take a look at another example. This example of a rock. So when we scan it, our XRF will give you all the possible minerals there, and you can color code them. It says, okay, show me iron. Make them every time there is an iron detected, make it red. Okay, every time there is a potassium, turn it green. Every time there's a bismuth, give me yellow. So you can select the different type of minerals that can be that can fluoresce and come up with a map. If I show you this map, what do you think it is? It looks very much like a cross section in an optical microscope or an SEM, right? You did not imagine that this is just an elemental map, not a structural map. But then that is the quality of results you can see. Now I'm going to show you what happens is this slide is about a molybdenum source, and when it excites these other minerals that come up. What if now I switch my source to a copper energy? If I switch to copper energy, you find that the iron will still fluoresce. That means all the areas in red looks the same. So that means iron is excited by both molybdenum as well as copper source. You look at the potassium. Potassium is also looks like they are mainly in the same region, excited both by copper as well as molybdenum. But if you start looking for bismuth that is found in the moly excitation, there is no bismuth to be found. You don't see the yellow thing coming out. But then you see blue. What's blue? Silver. So now silver is excited using the copper source, but you don't see silver over in the molybdenum scan. So what I'm showing you is this. XRF, if you have energy tunability, you'll be able to detect elements that may not appear at low concentration if you use the wrong energy. And that is the performance of synchrotron. Why people go to the synchrotron? Because they can always switch energy through the monochromator. So they can tune the energy in order to match the element of interest. That means you want higher sensitivity for the element of interest. You choose the energy that you want to measure the sample, and you can do that in the synchrotron. But you cannot do that in the laboratory until as a company, have found a way to make an X-ray tube that can be tunable in terms of energy. You can switch from one energy to the next energy. So that is the advantage of a tunable X-ray source. All right. So the next question is that how are we different from other micro XRF? Like for example, all the micro XRF that you see in the market, like Bruker or Pan Analytical or Horiba, they use what you call polycapillary optics. What is polycapillary optics? Which is a tiny glass tubing that are bundled together with many of them and make into a capillary optics. That means it is an optics made of glass fiber that are bent in a certain angle. And you can see this is not a true X-ray optics. It is just using a glass tube at the below the internal energy angle. uh, it causes the X-ray to bounce or to bend. So in other words, as the X-ray is go to the different capillary optics, there will be many bounces to before it exit at the focus spot. So what do you mean by that? If you have an X-ray that has to bounce many times over surfaces, so by the end of the day, when it comes out on the other side, the efficiency has lost 95 or 90 to 95% of its energy. So therefore, polycapillary optics, why have the ability to focus a bigger spot from, let's say, your X-ray tube. Your X-ray tube may be 500 microns or 100 microns in spot size. You can bring it down to maybe 30 microns or 50 microns by using a polycapillary optics. But the price that you pay is that the efficiency is going to be very low, and the point spread function, this means what is the resolution, the best resolution you can get out of that. Your spot size would not be better than 20 microns. Right. And you also need a very short working distance when you're using polycapillary. Short working distance meaning your optics have to be very near to the sample. So that is a working distance. This means you have to be very careful when you are doing such a short working distance that your sample is not going to hit against your optics. All right, SIGRAY have another implementation. This is our pattern. What we do is we have a twin mirror. This means this one set of mirror, this another set of mirror. So you see that how many bounces it has. It has one bounce and then two bounce and then it get into the focal spot. So what happens is the efficiency now is 85%. This means everything that is generated out, it will capture all the X-rays and then it's going to focus it down to a spot where you can get an efficiency of 85%. And the point spread function or the resolution on the spot is 3 to 5 microns, and you can operate this at large working distance. So because of this feature, we sell a lot of our X-ray tubes to the synchrotron, and we are using these similar ones in the micro XRF. Okay, another thing that you have to know about polycapillary optics is this. It is going to be very challenging for quantitative measurement. Why? Is because when you use polycapillary optics, the higher the higher resolution. This means the higher energy will go into a smaller spot, whereas the softer energy like K4 kb will start to spread towards the circumference of that spot. That means your spot, when they hit the sample, it has different energy. The higher energy will be at the center. The lower energy will be uh, at the outside circumference. So how does it look like in terms of the penetration depth, if that's the case? So if you have 16 kV, 16 kV is going to hit your sample much deeper and get you the fluorescence that are coming out from the deeper side of the sample. And if you have the small 4 kV, this means at the outside, so it only will be able to penetrate very little of the sample. So therefore, when you get fluorescence, you do not know where they are coming from, because did they come from the center? Did they come from the edge? Did they come from a certain depth? There is no idea about where they are coming from your particular spot, especially when this spot may be 30 to 50 microns. So, whereas compared with the SIGRAY system, which is achromatic, it doesn't matter what is the energy, all the energies are focused on the same spot. The only difference is that the higher energy will hit to a deeper side of the part of the sample, whereas the lighter energy will only come from the surface. So that is what the real optics will give you. So and then in terms of, let's say, the physical spot size, this is the size of a capillary optics here, 50 microns in diameter, and every one have different energy. Whereas the SIGRAY twin lens or achromatic advantage is that you can get you a spot size of less than 5 micron, and everything is generated, or all the fluorescence are generated out of that small spot. So here is a spot size. That means we can resolve elements that are 3 to 5 microns in diameter, and therefore you can, when you do a map, it looks like a SEM image or looks like an optical microscope image. So this is X-ray fluorescence, and now comparing the micro XRF of SIGRAY, the AtoMap, with the other techniques that you have. So let's say if I'm doing normal XRF, my normal XRF, I will be able to use a spot size of a few millimeter and excite my sample, but then you will not be able to get concentration better than tens of ppm. Like say this is 100 ppm, so the best sensitivity is just a couple of ppm from your XRF. What happens now if I want to use SEM? So if I use SEM with the EDS, you find that the SEM has a smaller spot size of a few microns in the spot size, but then their sensitivity is around 1%. In other words, if you want to measure things in your SEM and EDS, unless they are high concentration, like 1% or higher, generally you cannot detect those elements. That's the reason why you do not measure, let's say, elements in the plants or the tissue in the SEM EDS, simply because the native abundance of minerals in the plant, they are in parts per million. So therefore, it will not be easily analyzed. You cannot say what is the fluorine content of a plant or a leaf. SEM will not be able to do that well because their detection level is in the percentage basis, whereas the mineral composition or the elemental composition, they are all in the ppm level. So now what do you do? If I look at what you call trace level, let's say we put trace level at 10 ppm, the ability to measure things 10 ppm and lower, you find that there are not many machines that can do that. What are the machines that can do less than 10 ppm? These are wet chemistry, ICP-MS, right? You can get down to your trace level, sub ppm or ppb level, or the other one is a TOF sim. It can get down to very trace level, but then in general, these are all destructive techniques. So there isn't good destructive techniques, non-destructive techniques to measure trace level elemental composition. So where does that leave us? If we were to look at the atom map, see, the atom map can measure things down to your sub ppm level, very similar to your ICP, very similar to your SIMS, but then it can do the spot size of maybe 50 microns down to a few microns in terms of spot size. So that's where the detection level of AtoMap is in comparison with the rest of the techniques. So we can summarize something like this. If you have a SEM EDS or ICP-MS or XPS, you'll find that the detection level is around 1%. If you want to do low Z, it is very challenging. But then if you go to EPMA, which is a good tool in the geological section, the only issues in EPMA is that you need to have a flat surface. Your sensitivity is around 100 ppm. Low Z is going to be difficult. So that's where the EPMA is for geological application, and the speed to measure elements are very slow depending on the number of WDS detector you have. If you do ICP-MS, right, you find that the detection level can be sub ppm, but this is a destructive techniques because you have to dissolve your rocks into a solution before you can do your ICP-MS. And how do you find out the composition? You have to match the standard with the matrix. That means what is the ratio or the composition of the material that you're doing. Otherwise, your calibration curve is going to be bad. And ICP cannot detect your low Z, like carbon oxygen, your fluorine, your bromine, or all the halogens cannot be detected by your ICP. You can go to the SIMS, detection level is parts per billion, but it is a destructive techniques. It also have the matrix effect. So in conclusion, if you want to do this type of measurements at low concentration, you have to go to the synchrotron micro XRF, or the laboratory equivalent of the synchrotron micro XRF is the AtoMap, where we can simultaneously measure multiple elements. We can look at a spot size at sub ppm. We can run in vacuum or ambient. Your sample do not strictly need to be polished and flat. You can look at low Z, you can look at high Z non-destructively, and it has multiple energies or energy tunability, whether in the synchrotron or in the laboratory. So here's another example where if you're trying to look at biological specimens using ICP, low Z is not possible. There are no good solution because the sodium, the magnesium, carbon, nitrogen, oxygen, fluorine, silicon, phosphorus, they are no good solutions with ICP. And the other problem is that what about geology? Right? Geology has a problem, or compared with ICP, it has a lot of polyatomic interferences in the transition elements because you're using the analyzer in the ICP, which is a mass spec detector. So mass spec detector has a lot of polyatomic interferences, especially in transition elements and in the low Z elements like carbon, oxygen, nitrogen, fluorine, and silicon, phosphorus, sulfur, and chlorine. They have a low ionization cross section with ICP because of the mass spec detector, and also to a certain degree, all the halogens have problems together with selenium using the mass spec. So these are the drawbacks which we do not have in the micro XRF. So in other words, carbon, nitrogen, oxygen, fluorine, bromine are difficult or impossible using the ICP. So these are all complementary tools. So therefore, in many cases with our customers, they also have EPMA, they also have ICP, but they found that having an atom map actually is complementary and it will allow them to screen samples very fast and be able to detect at low Z, be able to detect at low concentration. So we have two models of the atom map, the ambient model as well as the model that has the ability to do high vacuum, where we can go down to boron detection. All right. So it will work with not only geoscience, it work with semiconductor research, work with biological material science or battery research. So the same tool will be able to cater for normal applications in the central research lab. So here's an example of imaging elements in the plant, which is very difficult to do. Normally, people go to the synchrotron. In this case, is an example of imaging the plant in the synchrotron, and we get similar results in the synchrotron. And also looking at some of these multi-element of, let's say, geometric these GMO type of applications where you are looking at elemental compositions in the accumulation of different materials like the zinc, iron, calcium, and potassium, and show what is the concentration of certain elements after according to the type of soil or type of fertilizers you put in, and also the type of modified crops that will selectively retain certain type of elements in their tissue walls. All right, sensitivity, like this is what you can see in the synchrotron. This is what we can see in our laboratory system. This is from EXRF, which is one of the top synchrotron in the world. So it has better detectability. Uh, but then this is the laboratory, and then which is not possible with the conventional micro XRF. Our system is also used in the advanced semiconductor research to look at the latest semiconductor devices at very low concentration. For example, this is a calibration curve of the thickness of cobalt, and we can see that the lower limit of detection is 0.03 angstrom, where you can plot the calibration curve. So in other words, the ability of us to track accurately different concentrations at the very low level allow us to use as a monitoring tool for advanced manufacturing. Many of you are very interested in rare earth. The problem is that rare earth is rare, and how do you find something that is not easily found because they are rare? And a lot of times the samples that come in is large pieces. So if you have a large piece and the what do you want to do with ICP-MS, or what do you want to do with SEM or other techniques, is going to require you to make a guess where to sample. It is not an easy solution. What if you want to do TEM? Where do you section this? Where do you fit this? So with the atom map, it's easy. We can put in the full 100 by 100 millimeter slab of rock into our system. You don't even have to polish it. You can, as long as they are not really very uneven, you can just put the rock as it is, and we can scan and map this at high speed at 5 milliseconds per spot. So therefore, you can now scan the whole sample at 5 millimeter per spot and then start to look at your element of interest, whether it's rare earth or whether it's gold or whether other things, you can do that. Right, these are examples of roots and so on. So here is an example, another example. You are scanning this whole sample for rare earth element, and if you color code yttrium to be yellow, this is done as 20 milliseconds, so you can see that all the yellow spots shows where the yttrium are found. So that way you can do a rapid scan of the yttrium or you can scan again. Once you located this, you can rescan again to get you better statistics and get you better resolution. So that will be the advantage of using a non-destructive tool to do your survey scan to localize where you want to detect. And after that, you might even say that, okay, let's go into ICP-MS in that region or in this region, or just look at EPMA to get you the correlation. So that will be the use of our AtoMap to rapidly identify large areas for geological exploration and for mineralogy. Next, here is an example compared with other type of uh, XRF, micro XRF. Like for instance, we are detecting for iron. This is what our system can get. We can precisely localize where are the higher concentration of iron versus where you don't have any iron or where you have iron that is at medium concentration. So that will be the clarity as well as the resolution. Whereas compared with other techniques, they will just tell you iron is everywhere and it cannot really localize which one is higher concentration, which one is lower concentration. That is a existing micro XRF tool. This is the information that came from BRIM after we have done their samples. Right, let's take a look at sodium. See, sodium, we can very accurately identify spatially where you have sodium, where the pockets of sodium, where you don't have any sodium, whereas compared with the commercial other commercial system, there is no comparison. Is because our sensitivity is much better than the conventional micro XRF. Now let's take a look at aluminum. Aluminum, you can see that we can see aluminum everywhere, including this region where the alternative system says that there isn't any aluminum there. It's because the detection level is just not there. So this is just a quick examples of how we compare with other existing micro XRF tool. Yeah. Okay, this is the same. These are the same. Now, here's another example of looking for different type of rare earth. Like this one is lanthanum, this one is cerium, this one is praseodymium, and this one is samarium. So we will be able to detect different things by scanning rapidly the sample and telling you, okay, where are the different rare earth element found. Do you know that you can also concentrate rare earth by growing plants that will absorb the rare earth and accumulate them in certain part of their plants? And one of these plants is called Saxifraga. So this is the work that is done by in the synchrotron by this institute in France that has bought a system after they have done this work in the synchrotron, and then they asked us to identify that in our laboratory. Nobody else can do that, but our system have been able to co-localize and get them results that is even better than what they got in the ESRF synchrotron. So this is where we look at the cross section, we see the yttrium, and then we even see oxygen, and we co-localize them in the root, in the stem, and is very similar to what they have obtained in the synchrotron. So that's the reason why they bought our system after the evaluation. Here's another example of looking not on rare earth, but looking at toxic mineral. Do you know that after a company have finished with its mining operation and they have left that region, the mines cannot be lived in. You cannot simply just say, okay, let's build some houses over this mining land, simply because when you have dug deep into the earth, you can get a lot of toxic metals or minerals that will come to the surface of the soil. So that's not a place that you want to build a house because people will start getting cancer. So one of the toxic mineral may be cadmium. So normally, in the normal course of time, after some a company leave the land and cease the mining operation, the land cannot be used for maybe 100 years, because that's the amount of time it may take for many of these toxic minerals to be leached away. So how do you speed up that time? One of the experiments or research project is to let's plant some crops that will selectively absorb some of these toxic minerals. And this one we call environmental remediation. This means you can use plants to mitigate or to reduce the toxic or to suck up the toxic matters or elements from the ground, so that you can remediate or you can bring the land to be more habitable faster. Instead of 100 years, maybe you want to cut it short to 30 years. So that way you can start building houses once more. And these are the examples we can do. Like we can see the cadmium is blue. So some of this accumulates in the root system, some parts in the stem system. So that will be something that can be done using this equipment, which is not possible with other micro XRF. Like for example, now what about looking for invisible gold? Gold that cannot be easily located because of their poor or low concentration. So we can do that in different steps. First of all, we can locate where gold is normally associated with. We can look for pyrite, right? So so therefore you scan and look for the pyrite first, and then rescan again in order to find where are the gold, right? So that way you don't waste your time by scanning every spot. So you locate where the pyrite is and then rescan it again and see where are the gold also located within the pyrite. So that will be one method. The other method is like what we talked about earlier, co-locating or co-localizing them with arsenic and with pyrite, iron and sulfur. So we scan and see where are the pyrite and the arsenopyrite. And then after that, we now start to correlate them, the whole region, where there are no free where there are gold that are free from pyrite, and also particles that contains pyrite, arsenic, and gold. And at the end of the day, what we want is we can co-localize everything that are overlapping. That means that contains the arsenic, that contains gold, and contains iron. So that will be one of the techniques we can use to for exploration to look at minerals that are in association with one another. Now let's take a look at the low Z possibility with this instrument. So you can see that one of the things about low Z is that if I have X-ray that excites deep inside my sample, you would not be able to analyze any low Z simply because the escape depth is too thick. This means the low energy carbon, your oxygen, your fluorine cannot escape from deep within the sample. So it will only escape at the surface. So that's the reason why what we want to do is those light elements, which by definition is anything atomic number 15, they have very low fluorescence yield. And therefore, the way you want to look at low Z analysis is that you need a vacuum, a high vacuum, and also you have to take into account the escape depth. So the rule of thumb is that your excitation energy for low Z has to be low in order to get higher fluorescence yield. Like for example, if you want to look at let's say carbon, oxygen, nitrogen, you want to use an energy that is not too high, so that you are just exciting the surface energy. and you want to have your atmosphere in the chamber to be high vacuum so that you don't the molecules of the air, the nitrogen, the oxygen, the argon is not going to absorb the fluorescence so that your detector do not receive anything. So X-ray transmission in atmosphere is going to be like this, where unless you use high energy, most of the time your detector would not be able to detect anything because the molecules of your air in the chamber is going to stop the transmission. So one way you can increase the yield for low Z is instead of just incidentally or having the X-ray to incident itself at 90 degree to the sample, what we want to do is that you want to have a ability to tilt the sample down to the grazing angle. So therefore, now you will see that the region of interaction with the X-rays will be mainly at the surface area, and in order for the low Z fluorescence to overcome the escape depth. So therefore, variable angle becomes very important for low Z analysis, and our system have a sample stage that can be tilted by the goniometer, right? That allow you to tilt up and down in order for the X-rays to come in at the glancing angle to increase your yield. So what is so unique about our low Z application in SIGRAY AtomMap is we have also a source, not only just the carbon, the chromium, not only the chromium source or the some of the copper source with lower energy. We have what you call a silicon source. Why is silicon source interesting? Is because in semiconductor they use silicon wafer. So if I'm going to excite something that contains a lot of silicon, my silicon peak has a huge background, and most of your light Z element, low Z element are below your 15 kV. So in other words, if you have a huge background from the silicon, your whatever that comes out will be masked, and therefore you cannot see them at all. So how do we solve this problem? We solve this problem by creating an X-ray source where silicon becomes the target. So when silicon becomes the target, now you have a clean because it doesn't cause the what you call the silicon do not excite silicon. So therefore, whatever you get is going to come from your lower Z element because the elements are transparent to their own characteristic line. So silicon-based source will not excite silicon. So due to this, when we remove silicon, what material contains lots of silicon? Geological sample, because you have a lot of sand, a lot of silica in most geological sample, and that geological sample will have the background if you use other sources. But if you are using a silicon source, you remove silicon as one of your major background. As a result, you no longer impede or prevent the analysis of the lighter element. So here's an example looking at let's say different type of samples here. Like for example, I'm looking at the is it fluorine? You find that you can easily see the difference of the calibration at 10 degree from the incident beam, and therefore the signal is much higher using the tilted geometry to analyze the detection of either germanium, detection of fluorine, or detection of any of your materials that typically will be masked by your silicon peak. Here's another example looking at fossil. This is not a SEM image. It's not a optical image. It is an elemental map. The elemental map shows the fish fish fossil, where oxygen is the purple one, the magenta. The blue color is your aluminum, and your green color is your calcium, and the red is your potassium. So therefore, you can even see oxygen. So that becomes interesting when you're doing mineralogy because you can now measure oxygen directly in your sample. So here is an example of a mineralogy sample where you see that this is a large sample, maybe 100 millimeter sample. You can see oxygen, which is blue, all the oxides. You can see the green ones is the magnesium, and then you can see sodium, which is difficult to measure throughout the sample. So and also the yellow one is your titanium, right? And the green is your potassium. So many different minerals or elements can be measured there, and then from there you can now do the mineralogy. So how do we do the mineralogy? We have our own software. It's not completed yet, but with the current version that we have, we bought a set of standard of from Ted Pella. Is a Geo standard, and it is have a whole set of minerals. So we just scan it, and we have been able to identify the majority of these minerals accurately. The rest of it, they are not identified simply because there are few possibilities. So that needs further iteration. But in general, everything else can be identified in the first run. So that will be the mineralogy of the system. Now, I'm not sure how important is carbon analysis for some of the researcher here because there is a global increase in the research funding for decarbonization, either in terms of energy, the carbon sequestration. One of the biggest industry is the iron and steel industry, where they want to uh, uh, do research how you can lower the carbon content and how you can capture the carbon. So if you want to look at carbon, you must be able to accurately measure carbon. So if your tool cannot get a good calibration curve to do carbon, it is not going to be useful. So one of the advantage here is this. You will be able to look at the carbon and we can create a carbon calibration where you can see that the A is 0, B is 0.089 of percent. This means it's less than 1%. We have been able to calibrate the carbon into a carbon calibration curve. And once you have been able to do this, now you can do your unknown sample and you can predict accurately whether your process or certain type of treatment is going to capture more carbon or less carbon. Another area where we can do that is looking at cement. Cement is found everywhere in every building. So what if you can use the cement to absorb the carbon in the air? So here's another funded project. The ability of using cement for carbon dioxide sequestration. Here's an example of a journal that has been published with one of our customers in the Journal of Petrology, where they compare ATOMAP with EPMA in some of their studies. Here's an example of an optical image of a geological slide. Here's an example of the MLA, which is the SEM EDS. Here's an example of the SIGRAY ATOMAP. You can see the big difference in terms of the resolution and the sensitivity of the different type of minerals within the sample. You can also use the petrographic slides that you may have kept. There may be hundreds or thousands of them. You can take out those slides and you can scan that with the XRF. And then from there, you can do elemental analysis and find out all the different composition of the different sections of the slides. So that again will be possible by using existing slides or new type of petrographic slides to do quantitative analysis. In other examples of volcanic regions where in the core, in the rim, or in the transition zones, how are the rock forming in their in their crystal structures, and what are the elemental composition of all the crystal structures. You can see that certain of them, you find that the iron is inside this rod or the shape of this thing. When they are in the transition zone, whereas in the when in the transition zone, whereas in the rim region, this means the outside of that rock, you find that the iron is inside those spindle shaped structure. So we also have done work where we correlated the XRF with XRM, X-ray microscope imaging, and combine them as a correlative technique. You can do that using the tools. That means XRF. You will do a what you call core localization with what you can get from your micro CT or from your SCM. And also, mineralogy is also used for exploration for oil and gas. You can look at production and sedimentology. You can look at petrology, or you can look at the diagenesis to look at the samples, where are the heavy minerals, and also use that to select for heavy mineral processing. So, in summary, the AtoMap can give you orders of magnitude improvement over conventional micro XRF or EPMA or SAM-EDS. It is comparable to what you can see in results from the synchrotron XRF. And how or why we managed to do that? Because of the innovation due to our multi-energy source that can be tunable, that are coupled with the high efficient optics, and also using grazing angle. You can do very high sensitivity, low Z analysis, and we have vacuumed as well as the same system can support many other applications. So with this, we can stop, and we are open to questions.
Right. Thank you very much, Mr. Low, for the informative presentation. Right. Pak Fika and others, if you have a question, then you can just ask directly to Mr. Low, or you can type it in a chat if you like.
Or you can ask directly, and somebody can translate.
Yeah, no problem.
Okay.
Yes, Pak Fika.
Can I? Okay, thank you, Kobi. Very interesting presentation from Mr. Low. I have some question for you. First is, as you said before, that the atom map using the multi-target material for X-ray source. Is that correct?
Yes.
Okay. So we can use some target material to get the good X-ray. My question is, do you have experience about what target material which is best for the rare earth element?
Okay, I think we have done some rare earth. So normally it may use the rhodium or the molybdenum type of source.
Okay.
We can experiment with the other source, but so far I think the rhodium and moly seems to be doing okay for the rare earth.
Okay, molybdenum and
And normally we use both of them. So that means you switch from one to the other to see which one is better.
Okay. Then my next question is, you said that when you use in the micro XRF atom lab, there don't need any preparation rather than SEM, we which is must or EPM, we must the surface must be flat. Uh,
Yes.
yeah, how the influence about the topography from the sample, if the sample was not not flat.
Okay, the reason why you don't need to do sample preparation for relatively flat sample, I'm not saying sample that is very jagged. Like for example, most of the rock slab is relatively flat, right? So in those cases, we can just use it as is. Like many times you get a slab that's 100 millimeter, right? Which is relatively big. Then you have to select how do you want to do that. For us, because this system can be used also for screening, so you just put the whole sample there. And why we don't need to polish is because our system has long working distance.
Yeah.
You know, this means your working distance can have a big tolerance. So because the working distance have a bigger tolerance, so the little bit of roughness is not going to really affect your results because the X-rays can still reach the detector. That is why there's a big advantage using our system, which are relatively insensitive to the surface roughness. So of course, you want the best quantitative result, then later you might polish that section. But for survey, we don't care. We just scan and say that where are the regions of interest where I should do my sampling. Does that answer you?
Yeah. Okay.
Mm.
Next, maybe skip. You hasn't mentioned about the detector. What detector you in atomic use?
We use the SDD detector. So,
SDD.
the SDD detector so depends on how what is the key is that we can bring our detector very close to the sample to get the biggest collection the angle. So you can tilt the sample in order to have a high angle of collection to increase our sensitivity.
How much the window area
The
for
The
the
window area, it can be, I'm not sure exactly whether it's a 10 or 20 or 30 millimeter.
then you mentioned that the result from the atom map can analyze using another software uh, in
What do you
Lampung.
mean?
Yeah, the result from the atom map,
Yeah.
okay, can be analyzed using another software analysis. Is this correct?
You can theoretically export our results to other mineralogy software. If you have a good mineralogy software, we can give you the format to export so that you can feed it into your own software. Like for example, we
Okay.
work with the Geological Survey in Germany. So they have their own software that's been developed over the past so many decades.
Okay.
So
Okay.
so so our software can be exported to see what they want or how they extract. So it is possible because our tool is structured like the synchrotron. Just a synchrotron, they go there and collect a lot of things, and they have their own software to analyze the results.
Okay. Do you have experience to convert with the map mineralogy software from
Mineralogy
thermal?
software, our own system we have our own mineralogy software.
Hmm,
And
okay.
if you have better mineralogy software, you're welcome to use them.
Okay. That's good. Okay. Next, For the validation from the analysis, I see that you using the CRM. Yeah. Do you have a CRM for rare earth sample, rare earth element sample?
Which sample?
Rare earth rare earth element
Yeah,
sample.
yeah. So what is it about the rare earth?
Yeah. Do you have a CRM, certificate material, for validate the result with the rare earth element sample?
Okay, we don't have if you're asking for the standards, are you asking for the
Yes, yes, yes,
standards?
yes. Yes,
Yeah,
perfect
we,
standard.
we, we, we don't have a collection of the standards. So if you have been doing a lot of rare earth, if you can also, if you want to do an analysis, you can also ship us some standards, then it will help to improve our results, to give you more quantitative data.
Okay.
So we can use the whatever standards you have because it's not easy for us to get the standards.
Yes, of course. Okay. I think for now I enough. Maybe another from the another. Thank you,
Okay,
Mr.
thank
Long.
you for all your questions. It's really
Thank you.
helpful.
Yeah, thank you, Pak Fika. I see some question on the chat room, Lau.
Yeah.
This one question, two question actually, related to the sample. How to prepare the sample needed for the mineralogy for this device, and is there a sample size requirement that can be analyzed? Like, what's the minimum and the maximum size?
Okay. Yeah. Good question. Do you need to prepare the sample for mineralogy? In general, we don't need the sample to be perfectly flat, right? There's no need to do coating of the sample like what you do in the SEM or EPMA because we are using X-rays. We are not using electron charged particles like electron microscopes or EPMA. So therefore, sample preparation is a lot easier than any other techniques. Right. Next is that what if your sample is in solution? Okay, sample in solution is going to be a problem with a vacuum chamber because you don't put liquid into a vacuum chamber. So you can still analyze them if you were to put the sample between the liquid sample between two Kapton layer or in a capillary tube so that it will not vaporize in a vacuum. So that is possible too, right? Uh, Next, sample size requirement, we can do micron size sample, several micron samples, small tiny piece of sample, or you can have a sample up to 100 millimeter diameter because our stage is X100 and Y100. This means you can put a piece of rock 100 by 100. Okay, so makes it easy, makes it what you call versatile to handle all kinds of samples. Or you can put a sample into a stage and put many different plugs within that stage so that you can program to go from one spot to another. Like for example, maybe in exploration, I have maybe 20 similar sample. I can put them into a sample holder that can hold all these sample plugs, and then we can analyze that overnight or analyze that over a long weekend so that when you come back, you can get all the different results without having to be physically there to change the sample.
Okay, right. Thank you, Mr. Long. Anybody else have some questions? Uh,
Okay, otherwise, I think you all recorded this, so
Yeah,
if anybody wants, they can always access the
yeah, correct,
recording. Yeah.
correct, correct.
All
Yeah,
right.
anyway, we record this session, and okay, if there's one question again come out in the chat room, Mr. Lo.
Yeah.
Limited detection, limit of
Okay.
detection, maybe it can analyze PBB. Can it analyze PBB range?
PPT.
PPB.
Oh, PBB will be the high PBB. We can do sub ppm and the high ppb, right?
Okay. If you wanna go lower, then you have to go for what is it? ICP?
Sims. You
SIM.
you
Okay,
go
yeah, SIM.
lower, you might go for ICP.
Yeah.
Your
Okay.
ICP MS might go lower, but it's destructive.
Yeah. Correct. Okay. Right.
Pak Bobby, I have
Yeah.
one question. Yeah.
Okay.
Yeah.
To
African.
can you? I still not understand about the comparison between the conventional micro SLF and the SIGRAY twin mirror lens, which is the point spread function, which is the conventional is more bigger, and then
Yeah.
the point spread function from the SIGRAY twin is more smaller.
Yeah. Yeah.
Uh, but the point is why for the Sigra twin can have a large working distance, uh, which is
Okay, it's
the point
because of
spread.
our it's because of
Mhm.
the optics. We
Okay.
are using a true X-ray optics so that the working distance is
Mhm.
more generous.
Mm.
Whereas the conventional micro XRF, they use the capillary tube.
Mhm.
The capillary tube requires them to have a very short working distance. It's a function of the optics. Working distance is always a function of optics.
So you said the efficiency using twin mirror lens is 85%. So
Yeah,
the rest is a loss on that process.
yeah. There's a lot of losses in the capillary optics.
So you mean that the conventional micro SLR right now have
Yeah.
lower precise result.
Yes, it's much lower results, lower efficiency. Therefore, they
Mm,
cannot detect what we can detect.
mm, okay. For the energy, you mentioned that the atomic can set from 5 egg and 16 key EV, right?
KB. Yeah.
Yeah. Uh, is any rule of thumb to use what kind of sample for that kind of the specific energy?
There is a what you call the what you have to take a look at the X-ray fluorescence cross-sectional U
Mm-hmm.
with different excitation energy. There are tables you can refer to. Therefore, certain elements, the cross-sectional U has certain energy range that give it higher sensitivity.
Mm-hmm.
Okay, the people who goes to synchrotron knows about that. So therefore, they tune their energy for their according to the sample of interest. Whereas for us, you would have to choose which one will give you higher sensitivity. So therefore, you have a few energies. You can run one whole set of results with one energy. You can run again with another energy, and then you can compare the relative sensitivity that way.
Okay. So we'll see the table, yeah, the
Yeah, you have to
fluence
see the
table, yeah,
table here.
yeah.
Right.
Okay. you hasn't compare about the with the micro city. Uh, what's the difference about this
Oh,
micro SRF?
microcity is the imaging system, structural
Okay.
imaging.
Mm-hmm, mm-hmm,
Okay, what microcity does is that it shows you the grain size. It shows you the crack. It shows you the void. So that's what microcity can do. So normally you may correlate that. Let's say I scan a rock, right?
mm-hmm,
I scan a rock, and then in the microcity is 3D.
mm-hmm,
So with 3D, I know that okay, there are certain areas within the rock that has a crack or they have a high Z, right? So, but my X-ray fluorescence cannot go all the way down there. So
mm,
how do I do that? Then I have to polish it down to where your region of interest. So the micro CT will give you the ability to look at the whole rock sample in 3D. And you can select then which region is of interest and then you polish it up to there and bring it to the XRF.
okay, okay.
Okay. So
SIGRAY,
it's
SIGRAY doesn't have a product for micro
no, we
city.
have a product. Do you have the time? I can quickly show you.
Okay, we have. I think we still have time or
Do you
Yeah,
have the
15
time?
minutes. I think.
yeah. Well, another 10 minutes, maybe
Yes.
10 to 15 minutes, because at this time we close to Friday prayer. So, well, another 10 to 15 minutes. Okay.
Okay, I can show you very quickly.
Maybe before you uh, show the information, Mr. Law, there's one more question in the chat room. Uh,
Uh-huh.
how deep can the analysis take place?
How deep the X-rays can penetrate maybe several millimeters of your sample.
Can
Because if
sample? Yeah, go ahead. Sorry.
yeah, because it will be maybe tens of microns you can go down through. Whereas your SEM will only give you maybe about 1 micron thick because your energy of the electron beam is not so strong. But then the XRF can go deeper.
Okay. Right.
Okay, here is what can you see the screen?
Yeah.
Okay, here is a X-ray microscope where you can use it for exploration, for core extractions, and so on. What we do is normally the laboratory characterizations of rocks. So with this, what is X-ray microscope? How does it work? You have an X-ray source, you have a sample, you have a detector. So when you shoot the X-ray there, you get what you call a radiograph or 2D X-ray, where the higher density material will look bright, the low density or the holes will look black. How do I do? This is what you do in your dental X-rays. You go to the dentist, the dental thing will image your teeth, right? Then how do I do this in 3D? In 3D, what you do is that you rotate the sample. As you rotate the sample, you get another slice at an angle. You rotate again, you get another slice. So what if you rotate 360 degrees and then you collect all those different angle images and use a software called reconstruction software? Then you turn this into 3D. But this 3D is a virtual or digital 3D object where you can see the surface, you can see what is inside there. So once you have this 3D image, now you can section electronically or polish electronically without physically destroying the sample. Like this, I can section one side, I can section again, I can section again. So at the end of the day, you will be able to look through the whole sample without you having to polish. Like for example, let's say I have this sample. If I do SCM cross section, All I have is that particular cross section where you can see information like here is brighter, this means it's higher mineral content or higher metallic content. You see that there's a void and there are cracks there. But then with the CT or tomography, what we do is that we can look at the whole sphere or the whole rock and say that, okay, how does it compare? You can now run it. So you can slice it down like you're polishing it down. Anytime you see that, okay, this is interesting, you can stop it or you can continue and stop it. And then, like for example, you can electronically, you can polish all these things. Maybe you come to a certain point, or a certain point which is interesting. Like for example, at this point, you say that, okay, this is interesting. Now, how I like this, I want to see what's the mineral content here. Then you can stop that process, look at the rock and how much it has gone through electronically. Now you can polish this section and bring it to your XRF or the AtoMap. And now you can do a mapping of the mineralogy as well as where the cracks are and whatever that you are trying to study. So that's how you can correlate between your XRF and your micro CT or X-ray microscope. So normally we sell those tools together. That means if you have the X-ray microscope, I can look at the whole rock in 3D. Then I can now section it into the right location where you think that the mineralogy is there. Otherwise, you just take a piece of rock, you only analyze the surface, maybe the top 100 micron. That is not good enough. But what if your rock is maybe 10 millimeter or 15 or 20 millimeter thick? Right? Maybe the thing of interest is not at the surface. The thing of interest may be two-thirds down uh, after you polish. So the X-ray microscope will allow you to do that just like what we are seeing. See, you can continue to go there. You see, every time you move, the number move, right? So it tell you how deep you have to polish in order to reach that location. All right. So this is all the way slicing or polishing it down to the from the top all the way to the bottom. That will give you the way we do correlation with a micro CT or X-ray microscope with a micro CT. All right. I'm going to show you some other examples. One of the big example is this. Let's say for oil exploration, we can look at different things. We can also use this to look at fossils, look at, let's say I have a piece of rock. I want to extract out the solid versus the spaces or the pore, and then we can do simulation. So this means you can separate out which is the solid material in the rock, which is the hole. So and find out whether those pores are connected to one another, and from there you'll be able also to find out many other application. You can look at, or you can take a piece of rock that is like a shale. You can burn it to burn off the carbon, and then you measure it again to find out what are the cracks and what are the network of the cracks for analysis, pore network. So these are examples of shale, and all of them can be done in such a way that, let's say I have a piece of rock and my piece of rock may be 100 millimeter, but then we have ability to capture the whole 3D image of that rock within, let's say, 5 hours. We can capture them like this, and be able to say that, okay, this is a piece of rock at 8 micron resolution. You can see that it's 25 millimeter diameter. I can look at this whole rock and look at it in 3D, or like for example, I can zoom in into this piece of rock to look at high resolution. This is now low resolution, even at 8 micron is expanded or magnified, but I can further zoom in into that particular area to see what is inside in 3D, or do slicing, electronic slicing. You can see that as we slice through the sample at 1 micron, you can see where are the microfractures and where are the mineral contents or micropores, where are the mineralogy of these things. And then you can physically section that and put it into your XRF or the AtoMap to find the mineralogy of that sample. Right. So these are micro system, and you can do that in very high resolutions down to 0.25 micron. This means we will be able to look at very small particles or mineralogy of that sample. But here's another example. We can look at it at high resolution with the biggest sample, this 2 millimeter. Then we can also zoom in on the big piece of rock and then look at what are the things at the higher resolution. Right. Here, this is a 400. This is a 1 millimeter sample, and then we can zoom into something that is maybe a fraction of 1 millimeter at higher resolution. Right. We can also use this for identifying the things that are buried in the rock that contains fossils. For example, right, this is carbonate, but you do never know that there is a coral that is buried inside the carbonate. And the X-ray microscope can actually segment out or take out what is this coral that is buried inside the carbonate. Uh, Okay, you can also do in situ application, imaging, where you can put in pressure, tension, or compression to crush that piece of rock and see where are the weakness, or and then how the crack propagate itself. So and also sample changer, or look at inside of a battery, or look at mineralogy, or even look at let's say soft materials like a piece of meat, or look at what is inside a fish like a dry fish, and give you information in 3D like what I'm showing you, and color them so that it looks more interesting for people. So you are actually seeing what's inside the sample without having to physically cut it. So one of the advantage of a micro CT or X-ray microscope is that it will help you to know where to section. It will tell you, okay, you should have to section so deep and then go to XRF or go to SEM, go to EPMA or go to ICP. So this will all be part of the sample preparation technique that we can do. All right. All right. So you can look at insets and polymers and many things, even though the density is very different. All right. So that hopefully give you a quick overview on the what X-ray
Overview.
microscope or micro CT can do for you. Okay.
Right.
Thank you.
Okay, Pak Fika. Sip, yeah. Okay. If you need more information, then you can just contact us, Pak Fika and others.
Maybe just last question. Uh, Mr. Lau, can you suggest to us if I want to buy micro city or micro SMF, what feature concern that we must know?
Okay. So sure, we will be happy to give you a what you call some of the feature benefits of each system, what that system should have in order to give you the benefit. We can work on that and give you a document on that. Okay.
Okay, thank you. Thank you.
Are
That
you
is,
applying for a grant soon?
yeah, we have some plan to buy some instrument, including the micro city and micro SRF
Okay. All right. And this equipment, where is it going to be placed?
in Lampung. In Lampung,
Lampung.
yeah,
Lampung is outside Jakarta.
yes,
Now the
in
island is
Sumatra
Sumatra.
Island, yeah.
Oh,
Sumatra
it's
Island.
Sumatra Island, not in Java.
No,
No.
but it's close to Java. As I said, it's
Okay.
another tip
All right.
close to
So
close to
you are
Java.
on the island, so I would love to visit you.
Yeah, you're welcome. Bahkan
Okay.
Pak Bobi kalau mau ke mampir.
Siap, Pak, siap. Okay,
Okay.
if there is no question, before I close this session, I think we have to have a photo of us. Please, everybody, a camera on. My my colleague can take a picture. Please, everybody, make your camera on. Or some people are very shy. Okay. Novan, sudah?
Ready,
Yeah.
Pak.
Ya.
Okay. Thank you so much, everybody.
Okay, Mr. Low.
Yeah.
Thank you very much. I don't want to delay your bedtime.
It's
Yeah.
nighttime here.
Yeah, I know. So that's why I don't want to delay your bedtime. So thank you very much for your time, and thank you very much for everybody to attend this presentation session. If you have any question, please feel free to drop us an email, or you can just ask me directly, or our other sales. Thank you again. Terima kasih.
Okay. Yeah. Bye-bye.
Assalamualaikum warahmatullahi wabarakatuh.
Selamat.
All right.
Terima kasih.
Bye. All right.
Bye.
Bye.
Bye.